Both are important. Regression is useful when you talk of a continuous variable which is plotted in a hyperplane or equation. In classification, it's about being able to identify an input belonging to specific categories which are known beforehand. So without further ado, let's start with this notion of linear regression. Linear regression is actually the simplest algorithm for predicting what we call as quantitative response. And in the simplest case, we talk about two variables, one input, one output. The basic idea is the output is a dependent variable, and then the other variable is typically termed as explanatory variable. So when only one explanatory variable is present, talk about a simple linear regression. In case where there are multiple input variables, explanatory variables yielding the dependent variable, then we call it multiple linear regression. So what typically we try to do by assuming a linear regression model is that we will try to fit a linear curve on the data, and then we try to guess what is the corresponding coefficients of the parameter which is to be multiplied for each of the explanatory variables. So basically we mean that we look at what is the equation of the form y equal to mx plus c, or y equal to m1 x1 plus x1 to x2 plus m3 x3, where x1 x2 x3 are explanatory variables. What are those m1 m2 m3? Those are what we try to estimate using linear regression machine learning algorithm. So as you already seen, we assume that the relationship between output dependent variable and independent what you call input variables, it could be any number, they are called regressors, whereas y is called the regressand. So an important element in this is that it is very often easy to get carried away by putting many different variables which are kind of on the left hand side without identifying the relationship between each of them. But statistically, there is a very important condition under these variables or choosing these variables. That is the notion of independence between the variables. So let's take an example. If you take an example like, let's say we're talking about let's take a situation where you're determining whether you are able to determine the average temperature for today. And that is dependent upon, historically, this day could have been, say, one of the three things. It could have been rainy day, it could have been a warm day, or it could have been a winter day. But that becomes a variable which need to do what is historically it's been. Second, what we look at is there any effect of cyclone? Is there a recent cyclone or something? That becomes another variable. Another could be, are you located in the northern part of the world where there's more cold? Or let's take latitude as one of the variables. Then we may get one more variable which is related to, are you in-house or are you going out of the house? So these are different variables which are all independent, which are all actually influencing the actual temperature, which is output. But you got to understand that there is a subtle relationship between each of them, in the sense, let us take latitude itself. Latitude itself could also have a dependency on whether cyclones are more frequent at that latitude. That means there's a dependency between the variable latitude and the variable. So that is something you have to be very cautious about when you're modeling these independent variables on the left-hand side, which are supposed to be forming the basis of the equation between your dependent variable and your independent variable. So that is the key message you got to understand when you're trying to create a concept which is linear in nature in the form of y equal to m1 x1 plus m2 x2 plus m3 x3 plus c. So as you can see, typically linear regression is about fitting a line to the input variables which are input to you in the format of points in the space, and then what you do basically is fit a curve for matching the output. And this is where the linear regression algorithm actually allows you to take the input data and come up with the right coefficients for the equation which is going to go into your final variable. So if you look at here, the different beta i's are what are estimated by your linear regression algorithm. So let us go to the Weka tool and start this algorithm, and we'll see how we can determine the linear model, which is a representation of the given input. Let's go to Weka. Let me open here. So you could start the Explorer. Now I'd like you to explore the data file called AutoMPG in your data file. So AutoMPG here is basically the file on which we're going to show the linear regression. And if you see here, we're talking about creating a linear model for the outward, which is called class variable, in terms of the different variables here. So let us look at each of the variables. Variable here can be either a continuous variable like displacement. Displacement is a continuous real variable, right? It can have standard value, it can be 1, 2, 3, 4, 5. Horsepower in the same way can be continuous in the sense it can have value like 3 horsepower, 6 horsepower, 8 horsepower. Weight of the engine can be similarly a continuous variable. Acceleration, on the other hand, could be same. It could be a continuous variable which can take any kind of value. But let us look at cylinders. Cylinders is actually a discrete value. Discrete value means that you cannot take any value. It has to take specific set of named values. So here we're talking about either it can be a 3-cylinder, it can be 4-cylinder, it can be 6-cylinder, 5-cylinder, or 8-cylinder. So in a typical linear regression, it is possible that you have both discrete kind of variable as well as a continuous kind of a variable. That is a typical problem which you will model. What is the final variable you want to capture here? That is always known as a class variable when you're doing a regression model in Weka. Here, miles per gallon is usually what we're saying is a function of how many cylinders a car has, what's the displacement, what's the horsepower of the engine, what's the weight of the engine, what is the acceleration, what kind of a model we're talking about. Is it old model like 70-year model, 75 model, 76 model? Then we have different labels for origin. So here, it's always a good idea to look at each of this data item and see the characteristics corresponding to each data item. In the sense, how many are of type 1, how many are of type 3, how many are of type 2. So that way, each field you can go and examine. If it's a continuous variable, you could find out what's the maximum, what's the minimum, what's the mean, what's the standard deviation. This gives you a visualization approach to the whole. So let's take a look at, say, origin. You see that the output, depending upon the origin, is kind of discrete. So now, when we talk about applying a regression algorithm, we can do this by choosing the classify button instead of clustering or association. So in classification, you can look at functions. There are several functions written here. We will be looking at linear regression. So linear regression is basically the method by which you want to do a curve fitting on your data. And then you start the whole process. So what you get here is basically a linear model, which is an equation of the type that miles per gallon is a function of minus 0.0359 into horsepower, minus 0.056 into weight, 0.012 into displacement, plus you have different representation here for the variables which are discrete in nature. So let me explain you what this actually means. This means that the first one, which is minus 2.2744 into cylinders equal to 6. If the data item has 6 cylinders, then you put 1 here. If the data item has 3 cylinders, you put 2 here. If the data item has 2, you will put 0. If data item has 4, you will put 4 here. If the data item has 5 cylinders, you will put 3 here. That's a cryptic way of working out a way by which discrete variables can be converted to continuous variables, and then you get an equation. Same way, if you were to repeat it again here, let us look at here. 1.2522 into model equal to 80. So if you have any other model, say 81, it will be 0 here. For 80, it will be 1. So it will be 1.2522 into 1 for the data item where model is 80. Whereas in case, let's look at this, where you're talking about 1.8307 into model equal to 77, 78, 79, 80, 81, 82, 81, 82, 80. Here, if the data item has model number 77, you'll put 1 there. If you have 78, you'll put 2. If it has 79, you'll put 3. If it has 80, you will put 6. If it has 82, you'll put 5. So that is a way by which it has discretized a continuous space into a combinations of the discrete values and substituting those values with appropriate cardinalities. So this is a very cryptic way Weka has been doing, but if you look at it, ultimately what you're getting is a curve which is linear in terms of the input variables. And then what you need to understand is we have here looked at a output known as root mean square error. Root mean square error is basically a collection of the entire errors in the system, in the sense how far is each point from the line you have extrapolated, and then you take that distance and you try to square it and sum it over all the points, and then you get the square root of that. That is what is known as root mean square error, and that is a very fairly commonly used metric for identifying how much is the deviation of the actual data from the model you have predicted. In this case, since we're talking about a straight line, it is basically the cardinal distance. It's basically the distance between one point and that particular line. And then we sum it over all the points in the input space. But then here, one important element we also forgot is that we are taking the entire input for creating your model. So what did we do earlier when we wanted to save the model? We said go into right hand side, right click, then you say save the model, where we can save the model saying that linear reg auto mpg 1. That is my model which I worked with, right? So this is the model which is containing the object file that actually has a representation of the straight line which has been derived. So if you want to run this on new data, you will have to load the data and then load this model and run it on that new data. But there is something which I want you guys to leave as a food for thought is, what is the risk with using the entire data for what you have for creating the model? You can think about it. We can take it up in the next class where we will be